Welcome to solverfy.
In a set of experiments on a hypothetical one-electron atom, you measure the wavelengths of the photons emitted from transitions ending in the ground level, as shown by these arrows in this figure. You can also observe that it takes 17.50 electron volts to ionize this atom. The first thing we want to know is what is the energy of the atom in each of the levels shown in the figure. That is, n is equal to 1 all the way through n is equal to 5. And then we want to find out that if an electron makes a transition from the n equals 4 energy level to the n equals 2 energy level, as shown by this blue line, what wavelength of light it would emit. So we know in this transition from this higher level down to this lower level that it's going to emit a photon of some wavelength. And we just want to find out what that wavelength is going to be. So we want to start with part A, and we want to calculate the energy of the atom in each of these levels. Because then part B, if we can just find the difference between the energy levels, the energy difference between these energy levels, we can then use Planck's relation to find what that wavelength should be. So to find these energy levels, let's first look back to the hydrogen atom, since this may give us an idea as to what the energy levels of our hypothetical atom are going to be. So the energy levels of a hydrogen atom is given by negative 13.60 electron volts divided by n squared, where n is a positive integer greater or equal to 1. So some important information we're given about a hypothetical atom that might help is this ionization energy of 17.50 electron volts. So recall that ionization corresponds to a transition from the ground state, n is equal to 1, to a state where the electron is in an infinitely large orbit radius, which is labeled by n is equal to infinity. And then the ionization energy, so this is the energy that needs to be put into the atom, the energy we need to give to the atom in order to strip the electron away from it, is given by E infinity minus E1. So just by looking at this relationship, this equation for the energy levels of the hydrogen atom, we see that as n goes to infinity, then 1 over n squared goes to 0. So E infinity must be 0. So our ionization energy then is 0 minus E1. And again, we can just plug in this relationship into this equation for E1. And we don't want to forget this important minus sign. We get negative 13.60 electron volts divided by 1 squared, which is just equal to positive 13.60 electron volts. So the ionization energy of our hydrogen atom then is just 13.60 electron volts, which already appears in our equation. So if we want, we can think about just substituting this in, and we want to just let EI equals 13.60 electron volts, then we can rewrite the energy levels for our hydrogen atom as just negative ionization energy over n squared. And now we can move on to our hydrogen-like atom. So H-like atom. And we guess that the energy levels of this atom are going to be negative the ionization energy over n squared, which is just negative 17.50 electron volts over n squared. Cool. So we can use this relationship, this equation, to go ahead and just calculate E1, which is negative 17.50 electron volts over 1 squared, which is just negative 17.50 electron volts. And E2 is equal to negative 17.50 electron volts divided by 2 squared, which is just negative 17, negative 4.375 electron volts. Awesome. And I'll leave the rest of these equations, energy levels, E3, E4, and E5, for you to calculate in a similar way. So now we have our the energy levels we wanted. En is equal to negative 17.50 electron volts divided by n squared. We can actually check to make sure that this equation is true, since we're given these wavelengths for these transitions. So let's go ahead and check that. So this we're given, let's focus on this n equals 2 to n equals 1 transition. And we're told that the wavelength that's emitted for this transition is 94.54 nanometers. So we can actually try to calculate the wavelength by ourselves using this equation and make sure that we get this correct 94.54 nanometers. So to do that, we recall that when we want to look at the emission of a photon when we go from n is equal to 2 to n is equal to 1. So let's first find the energy of that photon. The energy of the photon when we go to n equals 2 to n equals 1 is equal to minus E final minus E initial. Now you might be wondering why this minus sign is here. In the last part, when we were looking at going from a lower energy to a higher energy, this was a positive, because we were adding energy into the system in order to make that transition happen. But now we're actually removing energy from the system to go from a higher energy to a lower energy. So the the photon is being emitted out of the atom, so it's being taken away from the atom, so we have this minus sign. So we can also even rewrite this just as E initial minus E final, which is E2 minus E1. So we have the energy of our photon is negative 17.50 electron volts. And I'm going to just factor that out since it's common to both E2 and E1. 1 over 2 squared minus 1 over 1 squared, which is going to be, so we have negative 17.5 times 1 over 2 squared minus 1 over 1 squared, and that is 13.125 electron volts. So we have the energy now of our, there we go. So we have our energy of this transition from n equals 2 to n equals 1. So the energy of the photon that's emitted is 13.125 electron volts. But now how do we compare this to the wavelength that we're given, which is a wavelength, but we just have energy? We recall that the energy of a photon is given by h times c, so that's Planck's constant times the speed of light, divided by its wavelength. So solving for its wavelength, we have lambda is equal to h times c over energy. Now, I want to point something out. If you wanted to look up the equation for the value for h and look up the value for c, and just plug these numbers into a calculator, you'll actually get the wrong answer here, because we have our energy in electron volts, and Planck's constant has energy in joules. So to get around that, it's actually pretty easy to go from electron volts to joules. And that is an electron volt. So 1 electron volt, we can get that to joules by just multiplying the electric charge, which is so the electron charge which is 1.6. Here, I'll rewrite this somewhere where we have more room. So 1 electron charge, or 1 electron volt, EV, is the electron charge 1.602 times 10 to the negative 19 times coulombs times 1 volt. And we notice that the combination of the units coulomb, which is electric charge, and volts, which is electric potential, actually gives us joules. So we have 1.602 times 10 to the negative 19 joules. So now we use this value of energy. So we have EP is equal to 13.125 times 1.602 times 10 to the negative 19 joules. And we can just type that into a calculator. 13.125 times 1.602 times 10 to the negative 19 is equal to 2.103 times 10, 2 times 103 times 10 to the minus 18 joules. And now we can plug this in to this equation here, since now we have this in joules, and get our answer. So let's rewrite this. We have lambda is equal to hc over E, and we have E is equal to 2.103 times 10 to the negative 18 joules. And we know that H is 6.626 times 10 to the negative 34 joule seconds. And C is equal to 2.998 times 10 to the 8 meters per second. So we just type this all into a calculator. 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8 divided by 2.103 times 10 to the negative 18. And we get lambda equals 9.445 times 10 to the negative 8 meters, which is 94.45 nanometers. So clearly there was some rounding errors in there somewhere, but that's close enough, and that's close enough to confirm that we have the correct equation for our energy states. Awesome. So now we have just one more thing to do, and that is we want to find out what the wavelength of light will be, and we go from n is equal to 4 down to n is equal to 2. And this is actually going to be exactly the same calculation as we did from n equals 2 to 1, just with some different values for n. So Going a little bit more quickly this time, the energy of our photon is equal to E4 minus E2, which is negative 17.50 electron volts, times 1 over 4 squared minus 1 over 2 squared, which gives us 3.281 electron volts, which, if we multiply just by the elementary charge to give us joules, gives us 5.256 times 10 to the negative 19 joules. And then we can easily find the wavelength as we did before, with lambda is equal to Planck's constant times the speed of light divided by this energy in joules, which gives us 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8 divided by 5.256 times 10 to the negative 19 is 3.779 times 10 to the negative 7 meters, which gives us 377.9 nanometers. And there we have it. And we can use the same equation to calculate any of these transitions.